on our side, so we would like to present a small token of appreciation to Garud. So ma'am, can you just, on behalf of all of them, small.
Thank you. Thank you very much.
And request anyone, my PhD student, just from get this.
This is from the IT family.
Thank you. Thank you so much.
This is just one of my books. Which
Okay. Great. Oh, Aparna Gupta is there?
Yeah, Aparna is there. So this is something about decision sciences, what I wanted to just...
Great. Very nice.
And obviously the best one is the Alumni Association.
Yes, we got one when I visited last year.
Yeah, I know that.
All right. So yesterday we left off right here. We were talking about conditional PLSA, which is a way to do a non-negative matrix factorization on some data that can be looking as a conditional distribution. I won't get into details. I don't have a numerical example. Here's an example which has been taken from Barber, which talks about this conditional PLSA idea and tries to do some training exercises for that. So here's what they did. The training data consisted of, this was the training data. It consisted of convex combinations of base images. So these were the base images. These 4 base images were taken. You take convex combination of these base images and create this training data. And then from this training data, you relearned what the images were. So you rediscovered what is going to happen. And from this training data, if you did eigenfaces, you end up getting that. So the point here is that what they wanted to show was that if you did this conditional PLSA, you end up getting faces that look very face-like, whereas if you do the eigen decomposition, you end up getting things which don't look face-like at all. The eigenbasis for the first 4 principal components is in D, but it's not nearly as interpretable as the conditional PLSA. But of course we cheated. The reason there was a cheating going on was because these training was generated using convex combination of base images. In this one, and therefore the fact that it recovered back exactly those images is not as surprising. In the next one here, this is using positive combination of 49 positive base images. So here you 15.5a uses a positive, right. So on this side you have basically the PLSA base images. On this side you have on this direction you have 15, these are the eigen images, and this time these have been constructed using essentially the 49 base images, yes. So you take 49 base images in B, you recover, you take combinations of these guys, you recover using PLSA, you get up these constructions. So is a way what happens is that you, in the localized eigen images here, one sees more local structures like foreheads, chins, etc. The base images tend to be much more localized than the corresponding eigen images. So these are the eigen images, these are the base images, and in the base images what you're trying to do is that they're focusing on various parts of the face as opposed to an eigen image that lives everywhere. So the basic idea, what you're trying to say is, in this particular case, what happens was that in first case the 4 basis images were known. In the second case, you don't know how many basis images are there. So if you recover that, you end up getting that the basis images still perform reasonably well compared to the eigenfaces. The place where non-negative matrix factorization and conditional PLSA has been using a lot is modeling citations. This basically from the citations they wanted to create topics within citations as how are people or communities of citations. There are people who are citing each other and so on, and that ends up becoming an interesting topic. If you're interested, you can go and look at Barber's book, look at section 15.9. One very nice thing is Barber's book is available online. The entire book is available online. You can just download it and see what's going on. You can look at modeling the web. That's another example which is in 15.6.3 of Barber, and it'll give you an example of what's there. After we've learned how to do this conditional PLSA, you can start looking at different examples that might be happening. Okay, Next thing what we want to do is come to a different topic. So far what we've been doing with matrices is trying to explain the structure in the matrix. I have been given all the data of the matrix. I've been given the image. I have been given the citation index. I've been given the TF-IDF of the documents. The entire data is available to me. And what I want to do is explain that structure using some low dimensional information. Or I'm trying to say that modulo the noise, the actual structure in the matrix is low dimensional. And the rest of it is basically noise that fills up the rest of the story. This time around what we want is sort of inverse. I want to invert the story somewhat. I have a matrix and somebody gives me a smoothness property about this matrix. Somebody tells me that this matrix has low rank. Remember, in the first case what we were saying is I have a matrix, I want a low rank approximation to the matrix, so I will do an SVD. This time around, I'm given a matrix and given some extra information. The matrix has low rank. And using this extra information, I want to fill pieces of this matrix that was missing. Or another thing that I could say is I've got a matrix and I know that in the neighborhoods of this matrix, things are smooth. And again, I want to use this information to be able to fill in the data that is missing. So now these problems are collectively called matrix completion problems in the sense that I don't have the full data. Think about the following situation. So one of the interesting problems that you can think about, which is very practical, is you want to take the CT scan of a patient or a PET scan of a patient. Every time you expose this patient to radiation, there is a potential of some damage happening to the body. So what you want to do is every time you scan, in a CT scan, you get image in one dimension, or one linear scan is made. And if I tell you that the body's properties have some continuity, then maybe you can reduce the number of scans that you have to take in order to recover that entire information. So in this particular example that I'm giving you, there are two things that are happening. First, you never get a particular data point, you get an integral over that data point. That's your number. That is known to you. And you have some continuity property which says that as you move this integral along, things are not going to move discontinuously. So as a result, maybe you don't have to take every angle, you can skip a few angles and still be able to recover. If you want exact recovery, then this is not going to be possible. But on the other hand, if you say that you're okay with recovering within some noise, then perhaps you will be able to reduce the number of projections that you have to make. So that's sort of the spirit in which so we want to complete this matrix using some regularity property. We will talk about different things that are there, different stories that are there. Here's one very big example, which was this is a table that has been taken from Hastie, Tipp, Shirani, and Wainwright's Statistical Learning with Sparsity book. The excerpt of a Netflix movie rating data. The movies are rated from 1, which is worst, to 5, which is best. A symbol shaded gray circle represents a missing value, a movie that was not rated by the corresponding customer. So for example, this customer rates only 1 movie, that customer has rated 3 movies, and so on. And if you look at movies, this Catch Me If You Can got a rating from 3 people, Top Gun from 2 people, and so on. And what we want to do is fill this matrix out. And this is a problem that any of these recommendation systems are going to face all the time. You don't have ratings from everybody. I go to Netflix, Netflix wants to recommend something. I have rated a whole bunch of things. Now there's a very annoying thing that my mother was visiting me for a few months. She was using my Netflix account and watching Hindi and Tamil movies. Now Netflix thinks that I only watch Hindi and Tamil movies. So every time I go there, it wants to show me only Hindi and Tamil movies, no matter how hard I work. This just goes to show that if the number of ratings given by my mother overwhelms the number of ratings given by me, it won't know what to do. But in any way, we are trying to figure out how to do this story. Okay. So in many cases, in many applications, we have missing many or most of the elements of the matrix X. Consider that D by N movie ratings matrix with D movies and N users. Then X UI represents the rating on some scale. for user I for user U for mu vi. X will then be very sparse in that very few XUIs will be known. The goal is then to fill in or impute the missing data somehow. It has obvious applications in collaborative filtering and recommendation systems. Netflix gave out a prize a while ago. And there's another problem that is happening in this. We will talk about these neighborhood methods and matrix factorization methods in a moment. But there's another problem that has been happening in the internet world quite a bit, which is that people are actually unwilling to rate. If you ask them, give them a scale of 1 through 5, they're very unwilling to rate. So one direction in which things are going is also up-down. So you just get people to give it a thumbs up or thumbs down. They are much more likely to do that for you, which means that the information that you get about these matrices these movies have become very coarse. And yet, using that very coarse information, you want to be able to pick some more information, and therefore you have to start learning the structures that much better. I won't get into it, but this is one of the complications that has happened. So when this data set was given out by Netflix, which is about 7-8 years ago, I think, I'm not exactly sure, they actually had people rank from 1 through 5. And I think last year they switched from this rating to thumbs up and thumbs down because the participation rate of thumbs up and thumbs down is much higher. But now extracting information from that becomes a much tougher exercise. So we'll talk about these baseline estimators, and I'm going to talk about a little bit in the assignments as well. You can do some very simple baseline estimators. You can take the average of all the ratings of the training set, and put that in. You can introduce biases, so x hat ui, which is my prediction of the unknown component. So x hat ui, the hat will here refer to the fact that this particular component of that matrix was not known. This was the mean across all ratings in the training data set. These were biases that were added in for the user, and there is a bias for the movie, where bi is the average minus x bar divided by mi, which is mi is the number of users that have rated movie I. Bu is sum over I x ui divided by mu minus x bar, where mu is the number of movies rated by user u. So these are some biases that you can add to this particular thing, and essentially what you're trying to do in that particular case is choose bu and bi that minimizes the mean square error between x hat ui and the right hand side. Yes? BIs are biases. So this is a bias that is added for for movie I, and that is a bias that is added for user u. And you have to choose these to minimize the mean square error between the quantity that you know and the x bar, which is the mean. So if you just do the mean square error, you'll end up getting that these are the means. Use 7, and the other thing that you could do is you can add some, you look at, for all ui's, you can look at x ui minus x bar ui squared. If you remove this part, then if you just minimize this, you will get this as the optimal solution. If you put a regularization parameter lambda, where you're penalizing the norm of bi squared and bu squared, you'll get a number that is slightly different. And the residual matrix now is going to be x ui minus x hat ui. So these are my predictions using some baseline estimators. I do all that baseline prediction, and whatever is left over, I'll call that the residual matrix. And in that residual matrix is what I'm going to do something more clever. What does this, putting this lambda does? This is again done in order to make sure that I don't overfit within the training set. I don't want to find biases that fit too well within the basing set, and such that the test set performance becomes worse. So we'll continue to use movie ratings as a develop ideas. Neighborhood methods rely on calculating nearest neighbors. 2 rows are near neighbors if their corresponding users have similar tastes in movies. 2 columns are near neighbors if the corresponding movies obtain similar ratings from the users. To compute nearest neighbors, you use a distance or a similarity metric. Many a times we use cosine similarity metric, which is basically the cosine of the angle between the two, which is essentially like the correlation, because I have removed all the means and everything from here. So the top part becomes, without the renormalization, the top part is like the cross variations, the bottom part is like the variance, so this becomes like the correlation. So summation is only over users u that have rated both movies I and j. You can define DUV for users, U and V similarly. So this is for movies, you can do similarly for users, and then you can use for what you do is for a fixed movie U, you can rank all other movies in descending order of Dij. So you fix a movie I, you look at this cosine distance to all other movies, then the top L movies in the ranking are the L nearest neighbors of this movie. This gives you a new estimator, which is that the estimator is going to be, this is the baseline estimator, plus you take the average, this is the collaborative filtering term that you do over the neighborhood, where Li denotes the neighborhood of movie I. So why do you want to rank movies according to the absolute value of Dij rather than Dij when you're estimating this quantity? So let's go back a little bit. If you look at this angle, cosine, this angle ends up becoming, if this angle is between minus 90 degrees to plus 90 degrees, you'll get a number which is which is positive. If the angle happens to be greater than 90 degrees or less than minus 90 degrees, you'll get a number which is negative. So here we are saying that when you look at the distances, you look at the absolute value distances as opposed to the numerical distances Dij. So why do I care about absolute value versus without, which is the naked values? Why would I not just care about the what's that? No, but I'm ranking according to the absolute value. So down here, but on the other hand, when I do the correction up here, I'm taking the sign into account. In the denominator, I'm doing the absolute value, whereas in the numerator, I'm taking the signed values. What could be, why am I ranking according to the absolute value as opposed to just the number? So, okay, what I'm trying to say is the following. Let's say here's a particular vector of my movie, xi. Here's one movie xj. This is the angle theta ij. Right, so I'm defining to be the cosine of this angle theta ij to be equal to dij. Right? If I take this angle, right? So this angle is 180 minus theta ij. What is the cosine of 180 minus theta ij? Minus cosine theta ij. Right? So what I'm saying is that when I'm looking at neighborhoods, somehow this movie and that movie should be considered in the neighborhood. Why am I taking that particular case? Look at the numerator over here. I take the negative sign if I need to, but in the denominator, I take the absolute value sign. So what are we saying in terms of trying to find movies? So think about a movie, think about a particular user where I'm trying to predict what happens to that movie. So we want to take movies that the person, so let's not take this particular example, let's take, I'm going to draw a picture a little bit better so that it gives you an idea of what's going on there. So if I take a movie that looks like this and a movie that looks like that, okay, I'm claiming that when I'm defining neighborhoods of movies, I should consider this movie and that movie with somehow the same weight. So what does it intuitively mean in this structure? What am I saying in terms of information, in terms of collaborating with movies? If I take this movie, it means that that movie is very similar to the movie that that person has liked, and I would like to get some collaboration between them. But I want to include that movie as well because that is a movie that this person has hated, but there is information there. So this thing is positively correlated, that one is negatively correlated. Both of those pieces of information, negative high correlation and positive high correlation, both matter to me. So it's not, so Dij is almost like the correlation between the two. I don't like, let me go back. So like I said, Dij is like a correlation. I love correlations which are positive and close to 1, and I also like correlations that are negative and close to 1. It's not just the positive correlations that I care about. I want to move away from movies. I want to give a low rating to movies that have negative correlation with the current one. I want to give high ratings to the movies that have a positive correlation with what I have. But if I just looked at the positive value, then I'll only get movies that are positively correlated. There is also information in movies that are negatively correlated, and I need to be able to take that into account. And that is what is happening here. When I'm normalizing, I don't take the sign into account because the correlation, I'm only interested in the magnitude of the correlation, not the sign. But when I'm shifting my prediction of how much this person would like a particular movie, then I do take sign into account. I do take into account the fact that this particular value is positive or negative. You could easily use DUVs rather than Dij. So here we are using the discrimination between movies, and we'll have to adjust 11 accordingly. We still need to choose the value of L, and various obvious tricks can be made. You can use 11 to define a new residual matrix, then start working with predicting the missing element there, and so on. So you can basically add various kinds of extra things. And in the next module, and depending upon where we end today, I'll show you. I was going to give you a homework assignment to do this, but I'll show you the results rather than leave it for you because I will not be around to discuss it tomorrow. There's also matrix completion type problems. Here you want to minimize U0 and what is not O, that should have been I. So this is not O but I, Ui in omega. This basically says that these are the elements that I have measured, and I want to find a completion. So M is the completion that I'm trying to get, X, Ui are the measured points. I want to look at the difference between M and X on only those components that I have measured, and I want to make sure that the rank of M is very small. This would make sure that it will give me a filling for the other components as well. This is a very hard combinatorial problem, so rank is difficult. Remember, we solved this problem if all the data XU was available. Then I would just take the SVD of the X and take a rank R approximation of that SVD, and that would have been the optimal solution to the problem here. Here the situation is reverse. I don't know all the elements. I'm trying to find a matrix M which has low rank but approximates these elements reasonably well. And in order to be able to do that, the combinatorial problem is hard. Instead, what you do is you write a combination. This is the mean square error over the components that I know, plus lambda, which is a multiplier, regularization parameter, times M star, which is the nuclear norm or the trace norm. And remember, the nuclear norm for a matrix is defined to be the summation of the sigma I going from 1 through, let's say, R, where these are the singular values. And why do we use this norm? In order to get some intuition behind that, I want you to remind people, this is maybe something that you guys already know, but I just want to remind you what happens. So consider two different regression problems. Let's say y minus x beta plus lambda norm of beta squared, minimize over beta. Or another problem, minimize over beta, 1/2 of y minus x beta norm 2 squared plus lambda times the L1 norm of beta. So this one is called ridge regression, and this one is called lasso. So if you look at the difference between these two regressions, both of them are regularization type of methods. They are both trying to regularize the beta in terms of trying to control the out of sample performance by making sure that the beta doesn't grow. In this particular case, it is putting a 2 norm squared. In this particular case, it's putting an L1 norm. So when you look at this performance between these two, for a particular value of lambda, what is the difference in nature between these two methods? What happens here versus what happens there? So what am I saying? If I look at a particular value, here is lambda. If I take a particular value for a, this is say a particular beta I. If you use ridge regression, and on this side, what am I trying to plot? I'll say plot the absolute value of a particular beta I from there, and here it's lambda. So as I increase lambda, what is going to happen to betas? They will reduce, right? So they look something like that, let's say. It's not, I don't take this to be exactly the performance that you're going to get. You might get some performance like that. I don't exactly know. So both of them are going to do something like this. Now what will be the nature? Why do we like lasso as compared to ridge? What will happen in lasso as compared to ridge? Sparsity. Why? And sparsity in this particular case, what it would mean is that this parameter will actually go to 0 and stay put. Whereas in ridge, it tends to not go to 0, it goes to 0 asymptotically. It never goes to 0 exactly. Lasso just introduces and makes sure that those betas go to 0 exactly. And that is why we end up using lasso, because it also serves almost as variable selection. It automatically selects the variable to be used in this regression. This particular norm, which is the nuclear norm, does the same thing for matrices. It makes the corresponding singular value 0. As I increase my lambda, when lambda tends to infinity, this thing will be completely dominated by that term. And if you want to minimize the singular values or minimize the nuclear norm, all the singular values will turn out to be 0. So you'll get a matrix with 0 rank. As you take some intermediate value of lambda, it will introduce some of the singular values to go exactly to 0. If you had replaced this one by the Frobenius norm squared, which would have been the analogous situation for ridge, then when you get the singular values, they will never go identically equal to 0. They will asymptotically go to 0. And this is why people use nuclear norm as opposed to the Frobenius norm. The problem that has been set up there is basically lasso in matrix space. It's exactly basic. You're just doing the analogous thing for lasso, but in matrix space. And you end up getting some nice results from there. For those of you who have seen lasso, you can see that this is actually not you will see that even in lasso you have these S1 minus positive part kind of story, but let me walk through this. So let's define W to be UdV transpose be the SVD of a rank R matrix W. Then the soft threshold operator is defined as follows: S lambda of W. It takes the same singular vectors u, takes the same singular vectors v, but the singular values in the middle has been set as S1 minus lambda positive part to SR minus lambda positive part. S1 through SR are the singular values on the diagonal matrix D. What you do is you subtract a lambda from them and take a positive part. These projection operators, what they do is that if the element is known, the projection of that is just ui. If the elements are not known, then it's 0. Perpendicular, if the element is known, then you set it equal to 0. If the element is not known, you set it equal to x. So they are basically projecting a matrix X onto the known components of X and projecting X onto the unknown components of X. And there's an algorithm called soft impute, which has been implemented in a Python package called fancy impute, and I'll show you some results when we're done with talking about this. So all that algorithm does is the following: it projects it on the, or it takes the x, set x old equal to 0, and you iterate until convergence. All the places where the value is not known, you compute a soft threshold operator for these are all the values where the x is known, these are the values where the x is not known. For the not known values, take the old components, then you end up getting, do a projection on the x, find the SVD of this whole total thing, take the soft threshold of constructing it, compute the new x lambda, set x old equal to x lambda, and keep going. And this lambda is chosen through cross validation or validation test set approach. The soft impute requires a full SVD of the potentially large dense matrix in each iteration. Such a matrix can may be too large or even to store, but then you can say that you can use sparsity and low rankedness to be able to get these matrices all over again. So basically the story, I'll show you the result in a moment. Essentially what you do is basically do SVDs, you take the SVD of the matrix, then you shrink the matrix just like you would do in a lasso and repeat the whole story. There's a considerable theoretical work on determining how large that set gamma omega should be in order to recover x with high probabilities. The result depends on solution methods, depends on the rank, the distribution of matrix, coherence, incoherence, and so on. There are several other interesting instances in generalization: sparse Pca, robust Pca. So here in the robust Pca, what you do is you take the matrix X and you divide it into L plus S, where L has low rank and S has sparse. So over here we are approximating the matrix X as a low rank matrix. Here you can approximate the matrix X as a low rank matrix plus a sparse matrix. Lots of different things can be done. And there is 2 chapters in the statistical learning with sparsity by Hasty, Tipishari, and Wainwright, which is a good but quite technical resource. These techniques are starting to dominate now in very large scale problems because the amount of techniques that are available are very powerful as compared to these neighborhood methods that were there before. The next question that we want to talk about is reputation systems. There's ever increasing amount of online activity, and the data has been accompanied by decentralization of control. This is sort of a slightly different problem than the movie recommendation problem. So in the movie recommendation problem, you have this entire data set that has been given by customers that are assumed to be giving these rankings without any malicious motivation. They're not trying to motivate, they don't have intentions to force things to happen later on. But in many situations that we have right now on the internet, we want to be able to trust people, give some reputation scores to people where there might be intentions involved. IMDb and Rotten Tomatoes help us choose movies to watch. People just go there and rank. We need to figure out how much weight should we put on a particular ranker in order to say that that person's ranking is good. How do we decide what sellers to trust on eBay? Who should we follow on Twitter? How does Google figure out the importance of web pages? Why is Web so popular? And I'm told in India it's Zomato, which is supposed to be the most popular thing. Which one? There was some other website mentioned.
Swiggy and Zomato.
Oh, Swiggy and Zomato. Okay. One of my good friends has a big amount of investment in Zomato, so I know of Zomato. That again tells you about the bias in the information. So Swiggy is something I had not heard just because I have this biased source of information who claims that Zomato is the best thing. So what we're going to do is talk about this one simple PageRank algorithm, which is an algorithm that's been going around. And if you haven't seen this before, it's worth knowing about what this PageRank algorithm does. So in these reputation systems, one way you can think about is the problem that you're trying to figure out is what or who or what pages are the best. You have all of these pages on the internet, or all of these users, and the way you want to figure out is you want to reduce the dimension of this problem by saying, I want to focus on few pages, or I want to rank order pages, or I want to focus on few users and rank order them. And it's kind of a self-referential problem because the notion of best is not clear for these models. We do not know how do I think of something as best because the metric is not there. all the things that we were doing before, we had some independent metrics. We had a metric which says that somebody has ranked a movie. So for the movies that this person has ranked, I know what the rank was given, and I can try to find my reconstruction in such a way that it reconstructs these movies correctly. Whereas in sort of these page rank kind of story or websites kind of story, it's not clear what is the metric. So we'll consider Google's PageRank system. It's clearly of importance. It has applications to networks beyond evaluating the importance of web pages, and you can use it to highlight the ongoing challenges with reputation systems. So how do I define a reputation? So here's a big problem. I mean, essentially what many of these reputation systems say is that you're great if other great people think that you're great. But the problem with this definition is that the word great was never defined. We are somehow saying that you're great if other great people think you are great, but it's a very self-referential story. We don't exactly know. If I tell you this definition, it's not very practical. But in some ways, reputations seem to work this way. Even among your college cliques or your work cliques, very quickly, some people are deemed as great, whatever be the metric of great, powerful, popular, handsome, whatever your definition of great. Maybe handsome is not the right one, because there might be actually objective measures of what handsomeness is. But powerful and other things, there aren't objective measures. And yet we are able to somehow get this idea. So this PageRank algorithm is trying to get this notion. And here's way it's trying to do. So this is a very naive PageRank algorithm, and we'll check this. We'll do this PageRank algorithm slightly differently in the next page. So we say that I links to J if page. We'll put an arrow there. I goes to J if page I links to page J. Define CIs as the number of outlinks from the page I. So you look at a particular page. You look at all possible outlinks that are coming from there. Define CI to be the number of such outlinks from this page. Let xt 1 through d denote the page that has a web surfer has visited at time t. So pretend that there is a network of web pages. A user has arrived at time t in one of the d pages, and d is the total number of pages in the network. Now already there is a problem, because the number of pages d could be huge. So we have to figure out how we could scale up this algorithm to handle very large number of pages. Let's leave that for a moment. I'm just trying to build up a model. And then what you do, for the moment, let's say that CI is the number of outlinks. The initial model assumes that xt, the movement of this user, is a Markov chain with the transition matrix Q given as follows. Qij, which is the probability that xt plus 1 is equal to j, given that xt is equal to I. So at time t, I'm on page I. The probability that I'm going to go to page j is simply 1 over ci. Ci is the number of outlinks. We are just going to say that a person is equally likely to follow any of those links. And it's 0 if I is not connected to j. It doesn't go to something else. Now if this is a Markov chain, you can try to compute its stationary distribution. And what's the stationary distribution? It's a distribution over these pages, mu, such that mu is equal to mu times q. It's stationary under the Markov chain. There are problems with this. We'll come to it in a moment. Then we want to argue that I can use the stationary distribution as the importance of page I. So what does this stationary distribution essentially mean? Why do I think that the importance of page I could be given by the stationary distribution mu? So let's try to understand. There are other issues that it may not be unique if it's not reducible. If it's not reducible, there are all kinds of other issues. But let's say for the moment we give up on those issues. We'll figure out what to do with them. Let's try to understand why finding the stationary distribution might be a good idea. So if I start somebody at random on this network, on this Markov chain, what does mu I tell me? Have you seen people seen Markov chains before? Yes? No? How many of you seen Markov chains? Okay, maybe not too many. So let me take back my question and try to answer it. So in a Markov chain, what is happening? So let's draw a picture, and that way you'll get some idea, and then I'll motivate what this stationary distribution tries to do. So if everything is good, meaning this Markov chain is connected, you have some states, you transfer there, you come here, you go there, come back, maybe go there, and you keep going all over the place to this Markov chain. You're traveling around this Markov chain, which lives on some 5 states. Eventually what this stationary distribution says is that no matter where you start from, if you randomly sample this person's state after a long time, so you start the person off at some place on the internet, let them keep browsing, and at some point reasonably in the future, you go back and sample the state of this person, see which web page they are sitting at, then that distribution is given by that distribution mu. If mu is high of a particular state, that it means that it's very much likely that this person will be in that state. If mu is low, it means that a random person starting from a random location, the probability that you'll be finding them in that web page is low. So in some sense, this mu tells me how often are you likely to see a person who starts from a random location to be at that website. And that's a measure of importance of that website. This is what I call importance of the website. Now, why do I care about this being the right measure of the website? Remember, this measure of website has got nothing to do with the information on that website. That website might have no information whatsoever, but people just love to go there. And the reason this was actually done was initially when people were not gaming the internet. The PageRank algorithm was designed at a time where internet was not catering to entertainment as much. It was catering to information. And at that point, if people were repeatedly going to a particular website, the idea was that you're going there because you're getting some information. Google was trying to use this to index various things. So they wanted to, if you did a particular search, you looked at the corresponding Markov chain that is of relevance to that particular search term. You looked at what are the web pages that are ranking high on that particular search term, and you showed them that. Because you assume that the person is a random person searching for this particular term, and a random person searching for this term would like to see pages where the mu is high. Later on, they also figured out that these are the right places to put ads, because if this is the thing that is happening in search and you are actually recommending that people go to these pages, these are the places where people should be putting ads, because their ads will be seen by more people. Very soon after this algorithm came into place, people started doing something called clickbaiting, where you design a website knowing the algorithm. So how do I make this happen? Because in some ways, if there is a website from which there are lots of outlinks going, you can drag a lot of traffic in there, and from the outside it would look as if people are going to this website, but really they don't have any information. They come there and there's a clickbait where you're dragged into this website. So according to this stationary distribution, it looks like that website has a lot of traffic going through, but really it has of no importance. So this PageRank algorithm can be fooled into showing you websites which have no information but have a lot of traffic. Google quickly figured out what happens with that. So now the algorithm that they use, it's not known, because they also realize that the moment you declare some algorithm, there are people, and that algorithm has economic impact. People are going to try to game that algorithm. So it's now a game between Google trying to index pages and the other people trying to game it so that they can get more ads. We will not go into the details of that, just give you an intuitive feel for what that happens. And this is actually an implementation of this idea. You are great if other people think you are great. Why? Because if mu of a particular website is high and there is a lot of transitions going from that website to another website, the mu of that other website also will be high. So there is this notion of mu is high and you're connected to a high website, your mu will also be high. Alright, so this is a problem. This naive implementation is a problem because the mu will not be unique, it's not going to be reducible, and in general this is a problem because many websites will not have outlinks and there's going to get into trouble. So then here's a particular example from that particular page. Another less important issue with defining web page reputations in this way is that it's easily gamed by just a couple of pages that collude. See, for example, here's a paper that if you want to look at, making eigenvector based reputation systems robust to collusion. This is a paper by some people from Stanford. It's worth taking a look at how they do that. To resolve the uniqueness problem and make the collusion a little bit harder, what you do is you take a transition matrix which looks like this. This is the old transition matrix times 1 minus epsilon plus epsilon over d. So make sure that take an epsilon so that this particular quantity is positive. This can actually be written as the matrix is 1 minus epsilon times q plus epsilon over d 1 1 transpose, where 1 is a vector of all ones. In this Markov chain, what happens is that with probability 1 minus epsilon, you click on a link and you go to the other web page, and with probability epsilon you restart. So this epsilon probability says that you just restart from some random page. This one says with probability 1 minus epsilon you follow one of the links that is given on that page. Now because of this extra term, because you can start wherever you feel like it, implies that q bar is irreducible and therefore has a unique stationary distribution mu which satisfies this. And then you can, mu gives the page ranks for all the web pages. If you run the Markov chain for a sufficiently long time, then the proportion of time we spend on page I is mu high. The page rank or importance of a page is therefore captured by the importance of the pages that link to it. It's still a circular definition of reputation. Page rank has been generalized, manipulated, defended. Reputation systems in general have a cause of much litigation. Computing page rank is computationally intensive. Rather than solving 16 directly, this one directly, you use something called power iterations, which is the commonly used approach onto Monte Carlo, which exploits random walk interpretation is there. An approach that has been proposed for fast updating of page rank. There's also another story where instead of trying to define a page rank for let me see, it's not there. Instead of defining page rank for everybody on an average, you can start defining page ranks for individual people as well. You can sort of say that what is my individualized page rank, and there are codes out there that you can do to generate that. This page rank idea has been used for many places. Ordering returned by page rank can be easily adapted to reflect preferences for a subset. You can do this by changing the algorithm that with probability epsilon we choose a new web page randomly from C, and with 1 minus epsilon we click randomly on the link of the current page. This is known as personalized page rank. Page rank can also be applied in most network settings where there are links between nodes and some sort of preference. Recommendation systems form a bipartite graph with movies on one side and users on the other side. You add a link between a movie and a user if the user liked the movie. Now page rank gives the orders of movies and users. So what you do is you have a matrix now of you have a Markov chain that lives on users on one side and movies on the other side, and you link if there is a ranking between movies and users, you create a Markov chain and make it bidirectional, so you can go in either direction. And now you do this Markov chain, you again do this idea of which are the movies that are interesting. You get a stationary distribution in all of this. So suppose you do all of this, and then how would you recommend a particular movie to a user? So let's say that you pick up a user here. This is the user for which you want to recommend a movie. How would you recommend this movie to this user? What could you possibly be doing? So you have now a Markov chain living on users and movies.
So they count the number of users visiting a particular movie. Maximum will count the number which is maximum visiting a particular movie.
Remember, we don't want to do any counting anymore. I have a Markov chain. So why do I have done all the various calculations. So the counting is gone. I don't want to do counting. I want to use the idea of the stationary distribution and the Markov chains. So I've already linked it. I have put all of these links already there. I have run my Markov chain algorithm. I now have the rankings of the movies and the users. So for example, before we even go to this question, let's look at that. It will give you a reputation ranking of users and movies. It will tell you which movies are the most important movies. So if I don't know anything about a particular user, I would simply give them the movies based on the stationary distributions for the movies. Not knowing anything about the user, you could probably just say, okay, these are the movies that seem to be most liked by the population. I'll recommend them in the order of their stationary distribution. If I want to get a particular movie rated by a particular user, I would go and ask the user whose stationary distribution is the highest, because they seem to give rankings which people seem to like. So that's a ranking over users. But now if I pick a particular user, what do I do? How do I recommend this particular, for this particular user, how do I recommend a movie? So now for that particular user, I can look at the outlinks as somebody was suggesting. And then what do I do next? From
the link which have maximum number of rank, so I will recommend that.
So what you could do, look at all the links that this person already has, and then from there you recommend the highest level movie. But remember, if this person has already had the link, what does it mean? He's seen the movie.
So maybe in that cluster I recommend that.
Anytime you have a link from the user to a movie, they have seen it.
We can take the next
Reverse
question.
we can see the movie and the users who have seen it,
Yes?
and then whatever movie he has not seen, I can send him the same.
Perfect, good. So what you want to do is traverse this Markov chain, do a random walk on this Markov chain. So what you want to do is you want to go from here to a movie that this person has actually seen, to a user that has ranked that movie, and perhaps to a movie from there that this person has not seen. Now if you do it this way, you have a little bit of a problem that you have not taken into consideration the fact that this is not likely to be a very highly rated movie. This is just a random movie that this person could be recommended. At least what you're doing is you're going from a user to a movie, from a movie to a user that has ranked it, and from there to here. So now how do I make this so that I can take even the rankings of the people a little bit more under consideration? I don't want to use similarity because that is out of the domain right now. I just want to use page rank.
The user which has the maximum link.
Sorry?
The user which has the maximum link. Like
So I go to the movie, and then what do I do?
when you move the user, then you will see how many links you follow.
This movie has a many in links that are coming to them. So among those, I will choose the most influential user, go to that most influential user, look at all the remaining movies that user has, and rank order them in terms of their influentialness, look at the movies that this guy has never seen before, and order them. So once you have this idea of reputation, there are many things that you can play around with and decide what you want to do. The network can also be used as users and tweets on Twitter. This is used a lot to identify creators of tweets and followers. You can use such a system to identify influential people and make recommendations to users. Now the problem with this approach, as you can see, is it's gamed a lot. Twitter also has been playing around with these reputation systems a lot. They used to include retweets, but now they're trying to remove retweets because retweets, that was a very easy way of doing things. They were also I don't know whether this is happening at some point or not, but at some point you could hire a bunch of people who basically would create traffic for you. because essentially all of these things are driven by traffic, not by the content of the traffic. So as long as you create a bot that can just keep on generating traffic on your behalf, you can game these systems. And the same kind of questions that Google had to ask with its PageRank, now Twitter has to ask for its users, whether these users are actually true users, these are people that are generally just creating traffic, because that is what is being used by Twitter. Facebook has similar issues. I don't think in WhatsApp they are trying to do anything about ranking users. But it'll be an interesting exercise there to see what's going to happen. Okay, so that pretty much brings me to the end of the material that I wanted to cover. But what I want to do now is show you some codes, and then in the afternoon, in the first session, we'll go over the assignment that's there that will give you some more ideas. And then in the last session, we will switch to causality, because that's an interesting topic as well. What else did I want to show you here? I think I've showed you all of this. So let me actually spend some time going over the assignment that I was going to assign for this module that will give us some better understanding of where we want to go. So let's do with this one, so that I'll show you some codes associated with this one and then show you the examples from the other one later on in the story. So here's an example on collaborative filtering. This is an idea that we were using. We have a Excel database, which I'm going to show you in a moment. The workbook contains 100,000 movies rating from a movie lens database. The data consists of ratings from 1 through 5 for a total of 943 users from 11682 movies. These movies have been split into training and test worksheets. The test worksheet contains 9,430 observations for exactly 10 ratings per user. So you have this database as well. You can take a look at it, and here's where the database is here. So here's training, there's user, there is movie, there is rating that person has given to various movies. So user 1 has rated a whole bunch of movies, and they have rated them from 1 through 5. And the test set, we have taken 10 movies that this person has rated, and we want to be able to test what happens to them. The notes for this is the data in the train. Let me actually make it a little bit bigger so you can see it. Maybe 200%. Yeah. The data in the train and the test worksheets are train and test sets respectively, which together comprise of the data set. Which together comprise the 100K movie data set. There's also a 1 million movie data set that's also worth taking. There's exactly 10 ratings per user in the test set. The data in the two sheets are identical to the data in the UA.base and UA.test data sets, except we have taken a whole bunch of timestamps and other things have been removed. Okay, so for that data set, we want to be able to do various things. And here, unfortunately, I did not have the time to convert this into Python, so I'm going to show you a code in MATLAB that was written. The MATLAB code is available to you, so you can play around with that as well. If I can make it a little bit bigger, which is in view maybe. Where is it? How can I make this bigger? Editor, preferences. All right, so this one basically tries to do what we had proposed in the homework. So let me actually show you what's in the homework. So that's the data set. We're going to split the data set into two parts, training and test respectively. The test data set consists of 9,430 observations. We construct a baseline estimator where we use the average rating across all ratings of the training data, X bar. This is our estimator. Then we'll compute the test error for this estimator. Here in other parts, we use root mean square error to refer to the test error. Then we'll construct these biases for various quantities, and then we look at what the test error of this estimator is, look at whether these biases improve things. Then we'll use part B. Now we choose regularization and validation on the test set to choose the biases. That is, we solve this where the sum over the observation UI is over the training data. We choose a lambda greater than or equal to 0 to be that value which gives the best performance on the test set. What is the test set error here? We'll look at the various we'll be using, then we will put it on the test set to see what you end up getting as the right performance. 7 is an unconstrained concave optimization problem. This one, it's an unconstrained concave optimization problem because the two parameters lambda times bi squared and bu squared, they are clearly squared errors. The quantity in between, this x hat ui, this quantity is a linear function of bu and bi. So if you just look it up here, x hat has been defined as x bar, which is the mean, plus bu plus bi. So this quantity over here is a linear function of bu and bi. We are squaring that, so you get a contribution from here, you get a contribution from there. This is just like ridge regression. There is nothing more that's going on. This is just like ridge regression. So the first order optimization conditions are given by this quantity, and 8 and 9 are a system of m plus I linear equations and m plus I unknowns, and you will have a unique solution for any lambda greater than 0. You can either solve this function directly or use 8 and 9 to construct an iterative scheme. Each of them you can do whatever we want from here. So just to give you a little bit of details what's going on over there. What we have is the first term is basically the summation of x ui minus x bar ui plus bu plus bi, the whole thing squared. And then you have lambda summation of over I bi squared plus summation over u bu squared. So if you take the derivative and set it equal to 0 with respect to bu, you will get a linear term from here, you will get a linear term from there. You set it equal to 0, you'll get one set of linear equations. Those are exactly the linear equations that are set up over here. If you take the derivative with respect to u, you will get one set of equations which have to do, there the contribution is coming, bu will involve only those terms, only those movies that have been rated by u, bi will only consider all those users that are rating I, and from that you can set up this equation. Either you will look at a set of equations that way, or we will end up showing you how to do that. You get the best estimators from this A, B, and C to construct the residual matrix, and then we'll use the neighborhood method applied to the residual matrix to construct a new estimator, where Li denotes a neighborhood of size L. You can choose the size of the neighborhood via validation on the test set. What is the error of the test set now? So this is the big story, and let's try to see step by step how we can do this in MATLAB, and the same thing can be done in Python as well. So what I've been doing in the first one, I've just loaded the test set and the training set. In part A, I just take the mean of the entire training set, and on test set I look at the error between the test set and the x bar. So if you run in advance, you run this section, and where is the MATLAB windows that I have that I'm looking for? It's right here. We have all the data sets. So if I look at RMSEA, it's about 1.12. This is the error between the ratings that I computed using the means and the ratings that was computed, and the difference of the ratings with the mean versus the test. The next, in this particular case, for part B, essentially what we are doing is this summation. Let me actually show you on the slides what is going on, so that you have an idea of what's there. So BI is basically the summation, that's the bias that I get for each of the movies. It's the summation of x ui divided by the total number of movies minus x bar. Similarly, bu is the sum of over I of x ui divided by the total number of movies rated by the user I mu minus x bar. That's the optimal solution. And what we have been doing over in the MATLAB code is basically counting that. We are trying to find out BUB is the minimum across the various, the minimum of the training and the maximum in the training error of the first component, which is the number of users that I have, and the BIB, which is the second direction, which is looking at the number of movies that I have and trying to figure out what is the rank of the movies, and then counting them. So here I'm just simply counting them. If these two loops over here are just keeping track of which are the users that I have that have ranked movies and which are the movies that have been ranked by a particular user. If you run this one, which you have the code and you can run as well, and you can decompose what's going on. And if I look at the RMSE-B, that's about 0.9919. So just by looking at biases, you went from 1.122 to 0.9919. Now what we want to do is do this exercise of trying to figure out how to get the best lambda. And here we go. So here we have taken the lambda in ranges of in basically over they are going in logarithmic ranges from 0.01 to 1, 1.1 to 10, then over here, so here it's going in steps of 0.1, then a logarithmically increased from 0.01 to 1, from 1 to 10, from 10 to 100, and we are basically calculating various things. So these are, for each of these values of lambda, I'm going to compute what the various mean square errors are going to be and keep them in a particular matrix. In this loop over here, I'm constructing the various matrices that are necessary, and then I compute the biases by just taking A inverse B. So you can either do the iterative method, or you can do the method where I'm trying to get the biases based on a fixed value of lambda. Here I'm looping over all possible lambdas. For all possible lambdas, I find what the biases are going to be by solving the system of linear equations, or basically doing regression. And then I take the x test and x hat. X hat is my predictor based on the particular value of lambda. I look at the difference between x test, which is the leftover part, and x hat, which is my part, and find the root mean square error, record that, and then see whatever is the minimum of them. So find the lambda for which it's minimum, find the b's that are there that are the minimum, and then find the RMSE, which is put the lambda, predict the lambda where it's going to be there, and print the lambda, the test error, and so on. Actually, I guess the answer is already known. So if we run this section, at some point it's going to stop because it's going to take a little bit. I'm hoping that it's not going to be too long. Hopefully it will wake up at some point. And while that is solving, let's look at the last piece of this exercise. Where was it? And then we can actually see what's going on there. So the last one, so what we're doing right now is looking at this system of equations just by solving for various values of lambda, trying to figure out what's going on. Now we use a neighborhood method. Next part will be a neighborhood method. In the neighborhood method, what I do is exact same thing. I just choose a neighborhood. I just increase, I choose the neighborhood in steps of 1, and again do the same exercise, build a constructor, try to see what is going to happen in the test set. Now in reality, you would not do it this way, because what we are doing is right here. We are using the test set as the validation set right now. So in reality, what you would do is you would take the training set itself, divide it into the training set or test and training set, so that you can choose the best parameter and then use it on the final validation set as the right thing. But here I'm just cheaply using both of them together. Let's think if this thing has stopped. Yes. So not yet stopped. Yes, it should have printed if it had stopped. Hopefully it's going to keep on printing. Okay. I'm just going to talk about the last piece over here. There we go. So this is the plot that you end up getting for different values. So here's lambda going different values in steps. It's plotting what the minimum test error is going to be, and the minimum value of lambda turns out to be 3.9, and the test error there is 0.9585. That's what the minimum quantity turns out to be. And this is a pretty, the fact that you're getting this very nice minimum is coming from the fact that the optimization problem for the biases are very nice and convex, and as a result you get a very nice looking plot. And the minimum value, as we said there, it should have RMSED or C, RMSEC min is 9585. So by choosing the right shrinking parameter, the right ridge parameter, we were able to bring down the RMSE from 0.99 to 0.9585. The last piece, which is looking at the neighborhood, here. So let's do this. This is just defining the residual matrices, and then we will run this part. And here what we have done is we've chosen the neighborhood sets to go from 1 through 500. So from a neighborhood of 1 to a neighborhood of 500 is what I'm going to do. And I'm looking up here. I've already defined the various DKJs. The DKJs are the dot product of xj and xk divided by the norm of xj times the norm of xk, which is essentially the correlation between the residual matrices. And over here, we take the absolute values of the training. This is user I and movie J. We look at all the, in the training one, which all the things that have been, all the movies that have been rated by user I, and we take a combination of all the movies that have been rated by a particular user and all the movies that have been rated by all possible users. We take a combination of that, and instead of looking at just the D, we look at the absolute value of the D, we sort them in decreasing order, and we take the first L, which is L prime is the minimum of L in the length of dx. So depending upon what my L is, which is down up here, the L sets, we try to find, we put them into decreasing order. We look at whatever is the residual matrix that you end up getting, and that for particular length, we set the RMSE to be that quantity, and then again we do the same minimization. And just to give you a preview of where we are going to be once this whole thing solves is down here. The minimum value will appear at L equal to 72, and the test error there will turn out to be 0.9446. So instead of the test error, which is right now 0.9585, it will come down to 9486. All right, so I think we should, and then we will start back and look at a couple more examples of these dimension reduction, and then we'll go to understanding causality.